everyone, welcome. We are in the last two standards for functions that we'll be covering in Math 8. The first one, F.2 or 0.4 or B.4, is to be able to construct a function to model a linear relationship between two quantities. The second standard would be to describe what's going on in these relationships between two functions. So let's go ahead and get started. Very first problem, a car is traveling down a long steep hill. The elevation E above sea level in feet of the car when it is D miles from the top of the hill is given by the equation E equals 7,500 minus 250D, where D can be any number 0 to 6. We're going to find the slope and the y-intercept. I'm going to change this just a little bit. So let's think back to what slope and intercept means for linear. So for a linear equation, we're looking at y equals mx plus b, where this y value is helping us write this equation. It's helping us to understand what's going on. So if you remember, M stands for slope and B stands for y-intercept. So when we compare that to this equation, we could rewrite this equation so that they're in the same format. So if you look, my mx is represented by this negative 250d, and my y-intercept is represented by this 7,500. So what I can do is I can reorder these, move my negative 250 up front, plus my 7,500, and now let's identify. So the slope is my m value, which is in front of that x. So my slope is negative 250. My y-intercept is that plus b is listed right there. So my slope is negative 250. And my y-intercept, my initial value, is 7,500. So remember, slope is that rate of change. And it tells me that in d miles, so every mile, I'm going down 250 feet. That's what's happening. And then eventually, I'll reach an elevation of 0, and that graph would intercept the x-axis. Okay, so moving right along. Antonio and Juan are in a 4-mile bike race. The graph shows the distance of each racer in miles as a function of time in minutes. Who wins the race? So pause here, check out this graph, and decide who wins the race. All right, hopefully you've paused, and you would see that Juan would win this race. How do I know? Well, I know because the total race is 4 miles. It's a 4-mile bike ride. So if I look, Juan actually hits the 4 miles at 13 minutes, where it takes Antonio 15 minutes. So Juan would have the faster race time. The part 2 says, imagining you're watching this race and you had to announce it over the radio to write a little story to describe it. For instance, a story could be like, and they're off. Antonio has taken off, but oh no, he gets a flat tire and has to pause for a second. He's back in the race, but Juan has won. So when it asks you to describe a graph, It's asking you to kind of figure out what's going on. Describe what you see. So you'll see that in this next example. So Sophia gets on her bike. So let's go ahead and read this and then we'll create a graph. So Sophia gets on her bike and accelerates until she reaches a constant speed. She maintains that speed for 10 minutes. She then reaches a large hill where her rate slows considerably. She maintains this slower rate for 5 minutes until she gets to the top where she stops. Sketch a graph that models the relationship between Sophia's rate and the passage of time from getting on her bike until stopping at the top of the hill. Be sure to label each axis with the appropriate values. So she's going at a constant speed. So we know that she's going up and she's going up this hill. So we could say that the y-axis is her height or her elevation from the ground, where the x-axis is time. So here's where she starts, and it tells me that she's accelerating at a constant rate. And she maintains that rate for 10 minutes. So she maintains for 10 minutes, rate for 10 minutes, and then her rate starts to slow because she's reached this hill. She maintains a slower rate for 5 more minutes, so now she's 15 minutes in. So where she's at the top of the hill, and she stops. So now she's all the way off the ground. She's on top of this hill, and your graph would look approximately like that. Let's go ahead and read this next one. We're still looking at the standard F.2.4. So Joshua's mail truck travels 14 miles every day he works and is not used at all in the days he does not work. At the end of the 100th day, his work truck shows a mileage of 76,762. Fill in the blanks to express the mileage, y, as a linear function of the number of days that Joshua has worked. Well, we know that in y equals mx plus b, that m is our slope, it's our rate of change. Well, every day he's doing 14 miles. So my rate of change is 14. The b value is my y-intercept. So it's my initial value. And you might want to say, oh my gosh, well that's 76,762. But I beg to differ because this is the mileage at the end of 100 days. So to figure out where he started, I need to take the 76,762 and subtract out 100 days of driving. And if I subtract out that 100 days of driving, each day he drove 14 miles, so 100 times 14, I can rewrite this as 76,762 minus 1,400. And let's go ahead and calculate this here, if my calculator would like to work. So I would end up with subtracting 1,400, 75367. So my initial value is 75,376. Another way that you could look at this is I could fill in this equation. So at the end of 100 days, that would be my y value, 14x plus blank. I'm trying to solve for that blank. We know that it was 100 days, so I could fill in this 100 and I could solve. So same exact thing both ways. Which of the following is a correct interpretation of your equation? Go ahead and pause here and read through these. So your correct answers would be the number of miles Joshua drives the truck to work each day. They definitely gave us that, 14 miles per day. the mileage at the beginning of Joshua's first day of work. So I could figure out from this equation the mileage at the beginning of Joshua's first day of work, because this is how many miles he initially started with. So he started with 75,367 and he ended with 76,762. All right, moving right along. Brett wants to buy a 60-inch LED smart TV, so he opened a savings account and added money to it every month. The chart below shows the relationship between the number of months Brett has been saving and the total amount of money in his account. Determine the rate of change in this relationship. Rate of change equals slope. Slope equals m and y equals mx plus b. Slope also equals rise over run, or your change in x over your change in y. So when I'm looking at this table, my number of months is x, my total savings is y, so I can calculate this change. And I apologize, this should be the change in y over the change in x, so please forgive me if you caught that. Awesome. So the change, if I get my pen back, so the change in y over the change in x. So that change in y is 400, and I'm going from 160 to 415, and I'm going from 1 to 4. So I would end up with, if you have your handy dandy calculator out, you would end up with 255 over 3, which would give me $85 per month. So he's saving $85 per month. Determine the initial value. So if after 1 month he had $160, and I know that between 0 and 1 month I'm saved 85, I would want to subtract that out. So $75 is what he started with. So if we were to make this table, continuing this table, 0 to 1, we could figure this out. We know that this change is $85. So 75 would be where he started with. All right, I'm going to finish up the next few in the next video. So I will see you back there for the remainder of these slides.